Okay, so how are we doing tonight?
How are you?
I'm good. I'm good. Got my mason jar of coffee. It wasn't full, but it was more than half. Okay, it's fine. I wasn't going to sleep tonight anyway. So let's keep talking about chapter 8. I'd like to finish it. Let me mention a couple things. Let's see. Chapter 9. We're skipping chapter 9. I think I mentioned this at the beginning of the course. But there is a chapter 9 homework on WebAssign. It is completely extra credit. All right. And I will allow, if you earn more than 100% in WebAssign, I'll allow that to spill over into your full grade. So it is possible to get more than 100% in this course. That is a mathematical possibility. All right. I think I am going to cap, though. You can't get more than 10% on WebAssign. I did this one time, and I wasn't careful with how much extra credit I allowed, and somebody got like 200% in their in the homework, and it was just a little out of control. So again, completely optional, but it is available. I did also make a couple of the problems on the chapter 7 homework extra credit that weren't originally extra credit. They're the gravitational potential ones. Okay, questions before I launch into?
Will you post notes about chapter 9?
I will. Yep, I will post my lecture handout for it. I will fairly soon. Cool. Okay. So let's keep going. So I want to mirror this screen. Okay. Oh, come on. There it is. Okay. So, so far we've talked about torque, right? So torque is R times F times sine theta, right? It's the it's kind of a rotational equivalent of force, right? We've also written Newton's second law of rotation, which is that the net torque on something results in an angular acceleration of it, right? So if I want to rotate something, I need to apply a net torque. And the resistance of that object to rotation is its moment of inertia, I. And we have several definitions for this because it depends on what that object is. For point masses, it's mr squared, right? Or if we have a lot of point masses, it's the sum of mr squared for all of those. If it's an extended body, it could be some equation, but it's generally some kind of prefactor times an m and a mass or a distance squared. And as a reminder, that's things like, save that. Here. So clearly I've come to this a couple different times while I'm writing recording the pre-lecture videos. So we have an expression for this for lots of different objects, right? The one we use most often is half mr squared for a disk or a cylinder. Maybe the second most often is a long thin rod through its center. And this is not an exhaustive list, right? You could calculate this for all sorts of things. Okay. So let me go back very quickly because I want to say one thing about this. Okay, so we have two equations that contain torque, right? So if a problem says find the torque about some axis, there are at least a couple ways to go about it. If I have forces and where those forces are applied, it might make sense to calculate it using the definition of torque. But if what I have is a way to get acceleration, right? Or acceleration directly, and I know like mass and the some way to get the moment of inertia, maybe this one makes more sense, right? I also have two equations here, or two kind of ways to find moment of inertia, right? And it's not uncommon for me to see like a problem will ask, find the moment of inertia of this thing. And a student will try their best to use this equation, but they don't have enough information to solve that equation. But maybe they have enough information to solve it this way. Does that make sense? It's also not uncommon to have a series of questions about the same setup that has you solve for the moment of inertia one way and find other information from the other definition of moment of inertia. Does that make sense? Okay. Okay, so let's look at a couple of problems. So let's go back to chapter 8. I have my list of things I'd like to do. I'd like to do example 5. So example 5 says we have a 3 meter long 100 Newton board sitting on 2 supports, one at the left end and the other is 1 meter from the right. And we got a paint can sitting on the far right end of the board. So let's draw that picture quickly. Yeah, that's perfect. Okay, so a 3 meter board, that's 3 meters, great. And a support like right here, and a support 1 meter from the other end, so that's like here, and a paint can sitting at that end, right? And again, I can label some distances here. The full length, good grief, is 3 meters, and this is 1 meter. And the questions are, there are 2 of them. One is, what are the normal forces from the supports? And what's the heaviest paint can that can sit on the right end of this without making it tip over? Okay, does the setup of this problem make sense? We've got 2 supports. They're splitting the weight of this system, right? But it's not clear that they're splitting it equally, right? Because I've got, let's see, you could imagine a simple situation where it's pretty obvious by symmetry that each is supporting half of the weight. Like if you had a board supported by each end and it's a uniform board, if this has a weight of 100 newtons, pretty clearly each of these is supporting 50. But if you moved those, right, one like over here, now it's not entirely clear. I have a gut sense that this one is supporting more than that one because it's closer to the center of mass, right? Imagine like you're supporting your pencil, not the expensive pencil, but the one I got for free. If you had one finger closer to the center of mass and the other off to the side, pretty clearly the one that's closest to the center is supporting most of the mass, right? So that gives me a sense of like which one is bigger, but I'd like to actually do this in a mathy way, right? So let's do this in a mathy way. Come on, golly boy. Okay, so we can draw a free body diagram for this. We've pretty much already drawn it, but let's just be a little more careful. That's not a whole lot more careful. We have a center of mass of the board, right? So there's weight acting down there. That's the weight of the board. I also have a weight of the paint can acting right over here. Weight of the paint can. I should have a normal force on this side, call it like normal 1, and a normal force like right here, call it normal 2. And I don't know off the top of my head which one is bigger, normal 1 or normal 2. There's probably a way, because normal 2 is closer to the center of mass of the board. Yeah, it's probably supporting most of the weight. But we'll let the math show us that. So we can fill out Newton's second law for this in the y direction. We can say equals m times a sub y, which is 0 because it's not rotating. So I can say normal 1 plus normal 2 minus weight of the board minus weight of the paint can equals 0. But that's two things I don't know in one equation. And typically when we see this situation, we say, all right, let's use the other direction. Well, in the x direction, I get 0 equals 0, which doesn't help me at all. So what I'm going to do is do sum of the torques equals 0, because, and that's like barely legible. I just don't want to rest my hand on the, yep, that's why. So I can use, got it, piece it, okay. The sum of the torques equals I times alpha. But again, the system's not accelerating, so alpha is 0, so I don't even care what the moment of inertia is, which is great, right? So the sum of the torques equals 0. But remember, torque is defined about some axis of rotation, so I need to pick a location to be the axis of rotation. And there's no obvious point in this problem to serve as the axis of rotation, right? Because it's not rotating about any point, which means the sum of the torques about every point in the universe is 0, right? So I could pick, you know, my childhood home in Galva, Kansas to be the center, the axis of rotation of this. But that doesn't help me because whatever torque I calculate is going to have N1 and N2 in it. So it's the same two things I don't know, just in a different coordinate system. So what's going to be useful here is if I choose like one of the locations where the one of these forces is located. We saw this yesterday, that when I put the axis of location at a force, the torque due to that force is 0, right? So I'm going to pick the left hand. So I say at the left side here, the sum of the torques equals 0. So I can say the torque due to normal 1 plus the torque due to the weight of the board plus the torque due to normal 2 plus the torque due to the weight of the paint can all equals 0. And again, this is true about every axis, but now I'm going to fill in torques about the left-hand axis. So let's make this dot go away. No, not the force, just the dot. Just, no. I win. Okay, so let's label some radii here. Let's make them red. So if this is my axis, what I care about is the distance to there. So that's R for the board. There's R for normal 2. And there's R for the paint can. No, I want R for the paint can. Right? And those R's all depend on my axis of rotation. So if I picked a different axis, I would have different R's, all right? In the interest of time, we may not get to that part of this problem because I have a lot of stuff I want to talk about tonight. Okay, so I can fill in. I can say, first of all of the angles between R's and forces is 90 degrees. Do you see that? Every theta is 90 degrees, which means all of the sine thetas are 1. So I'm not even going to put them in the equation. All right, just to keep from confusing you, normally you would say RF sine theta. That's the definition of torque. But again, all of the thetas are 90, so I'm not going to muddle my math with that extra bit. Okay, so R normal 1 times normal 1. Okay, and then R for the paint can times the weight of the paint can. Now I'm going to be careful here. The weight of the paint can acts down, and around the axis we've chosen, that's counterclockwise. So positive is correct here. All right, but when I get to R for normal 2 times normal 2 is actually going to cause clockwise, counterclockwise. I had that backwards. Sorry, guys. The weight of the paint can causes clockwise rotation. I forgot how clocks work. It's fine. So that one should be negative. Minus. And then the normal 2 wants to cause clockwise rotation. And then the weight of the paint can normal 2 causes counterclockwise, so we called it positive. The weight of the paint can causes clockwise rotation. Again, I'm just looking at, let's use a different color. I'm just looking at the axis of rotation and the kind of, the direction of rotation that each of these wants to cause, right? And we call counterclockwise positive. The math would still work if you called clockwise positive. It would just change the sign of everybody. Oh, sometimes more ink doesn't help. Nope, it's getting worse. I just need to stop coloring. Okay. So our last is the torque due to the paint can, which is negative R paint can times the weight of the paint can equals 0. Okay. So the R for the normal force is, for normal 1 is 0, right? So I'll say 0 times normal 1. That's why we put the axis there. Minus R for the paint can, the board is, let's label those quickly so we can just finish this up. So that's half the length, that's 1.5 meters. R normal 2 looks like 2 meters, and R for the paint can is 3 meters. You guys buy that? The full length of this thing is 3 meters? Okay. Okay, so we're almost there. Spend half the class doing this one problem. It's okay. It's good. 1.52. So 1.5 meters times 100 newtons. We were given the weight directly, not the mass this time. Plus, what was this? 2 meters times normal 2 minus 3 meters times the weight of the paint can. What was the weight of the paint can? Over here. Oh gosh, what am I doing? 25 newtons. Okay, great. Okay, so we can solve this then for normal 2. And what I get for normal 2 is 110 newtons. Questions about that? So that's not the full answer, right? The full answer is what's normal 1 and normal 2. And then there's another part to the problem, but I'm not going to do that one right now. So what is normal 1 then? Well, I could either do exactly the same thing I just did, but move the axis of rotation. Let's choose a different color. I could put the axis of rotation here, right? That will zero out in 2 and let me solve for in 1. And there's utility in doing that, but look, I already know that in 1 plus in 2 minus the paint can minus the weight of the board has to equal 0, right? In the y direction. So what are those things? Well, that's normal 1 that I don't know. Let's change colors. Do blue. Normal 1. We just figured out that normal 2 is 110 newtons, and the weight of the board is 100 newtons, and the weight of the paint can is 25 newtons, equals 0. Doggone it. I can't fit my 0 in there. Put it on the other side. There. Right? So what do I get? 110 minus 100 minus 25 is going to be 15 newtons, right? That's the remainder. So N1 is 15 newtons. Oh, I didn't get 15. Why didn't I get 15? Oh, because I rounded. Doggone it. This is a rounded answer. And if I round, that is correct. What I actually get if I don't round is 112.5 newtons, which means normal 1 would be more like 12.5. Hey, if you get a different number than I do while I'm working on something, you can interrupt me. It's totally fine. Okay, so I'll ask questions. So this is just a dynamics question. This is just really it's a statics question, right? We're applying the sum of the torques equals I alpha, but alpha is 0 in this case. I worked 2 examples where alpha is not 0 on the pre-lecture videos, so I'm not going to do any more of those right now, I think. In my notes, I have to do 11, but I think I don't want to do 11 because I don't want to, I have other things I want to get to. So let's do another problem. Let's look at example number 10. Example number 10 says, let's say you hold a meter stick this way and you let it fall to the floor, right? In a way that it like rotates around this end. So you like set it up and then give it a little bit of a tip and then it falls. Right, so it's gonna fall and hit the ground here. The question is, how fast is the end of the meter stick going when it hits the ground? So we could think of this in terms of force and force causing torque. So we can even say, okay, throughout this motion, it's gravity causing this, right? So we could think of gravitational torque, and we could say, well, I know that we treat gravity like it's acting at the center of mass. So there's the weight, and that's causing some torque. But is that torque constant? Meaning, is this angular acceleration a constant angular acceleration? And the answer is no. The angle between r and weight changes constantly through the entire motion, which means the torque is always changing. It's a maximum when it hits the ground, and it's a minimum when it just starts, right? In fact, if you don't give this a little bit of a tip, it won't move at all, because weight is down and r is up, so the angle between those is 180 degrees, and sine of 180 is 0. So there is no torque unless you're just a little off axis. So what this means is kinematics doesn't help us here, because kinematics depends on alpha being constant, and here alpha is not constant. So it's like, are we shot then? Is there any way we can solve this problem? Well, I hope so, because I put it on the lecture handout. Yeah, there's a way we can solve this problem. We can use energy to solve this problem. All right, because what are we doing? We're changing gravitational potential into rotational kinetic energy, right? And I haven't talked about that in a Zoom lecture yet, but I did post a video about it for today. So rotational kinetic energy is half I omega squared. All right, you can derive that in a very analogous way to how we derived regular kinetic energy. This is not a different unit. This is, I say rotational kinetic, but it's just kinetic energy due to rotation. All right, but the unit here is still a joule. All right, so if I have a rolling object, the total kinetic energy of a rolling object is the linear expression plus the rotational expression. So I'd have to do half mv center of mass squared plus half I omega squared to get the total energy of that thing. All right, okay. That goes away. So we're just doing conservation of energy here. We're saying K initial plus U initial equals K final plus U final. So pretty clearly, the initial kinetic energy is 0 because it's starting from rest. And it's going to end up on the ground, so we could call that U final is 0. So all of its potential energy is becoming kinetic. But we're used to, when we say potential energy, this is gravitation, so we say mgh equals half I omega squared. But what is h? because the meter stick is actually everywhere between the ground and 1 meter, right? It has mass along the entire length. So I guess strictly speaking, we should integrate it. But if you do that, what you'll see is gravity acts like it's all acting at the center of mass, which is how we define center of mass. So what you can use for h is the height of the center of mass. So this h is going to be h for center of mass, which for a meter stick is half of a meter. All right? So make that go away. So at this point, we can just plug in. Or can we? Because what is I? Let's use a different color. What is I? Well, I is the moment of inertia for this thing, and this is a rod about its end, right? So that is this one, right? A thin, long rod with rotational axis through its end. So it's 1/3 ml squared. So that's what we're going to use here. Where am I working? Right here? So it's 1/3 ml squared. How long is a meter stick? Anybody? Okay, I'll guess then. So mass times 9.8 meters per second squared times 0.5 meters equals half. It's the worst half I've ever written. Half times 1/3 ml squared times omega squared. But I'm not looking for omega. I'm looking for the velocity of the end of this thing. And remember, v equals omega r. So I'm looking for v at the end. So r is going to be 1 meter, right? So I'll put this in here. So L is 1 meter. I'll put L in for R as well. So that's omega is V over R. So that's V. Is that what I want to do here? 1/3 ml squared equals omega squared. Yeah, V squared over L. This is V over L squared. So it looks like the L's go away, which is interesting. So I can cancel out the masses. That's good because I didn't know the mass of this meter stick. The L's go away too. Again, kind of interesting. So if I solve this for V, what I get is 5.4 meters per second. Oh, come on. Questions about that? Again, I worked a rotational kinetic energy example problem in the pre-lecture video for this. Okay, there's one more concept in this chapter. So let's talk about it. And that last concept is angular momentum. So let me remind you of angular momentum. Again, it's in the pre-lecture video, so I'll find the scratch for the angular momentum. So we basically have two equations for angular momentum, and we use the letter L. L doesn't look very nice though. The letter L, lowercase or uppercase. Often uppercase means the I omega version, or it means total angular momentum, whereas the lowercase l is typically for a single object or for a point mass. So very quickly, when we think about linear momentum, you think about it in terms of collisions. I think I said this in the video. It's related to how hard it is to stop something, right? So a massive thing traveling mediumly fast or a light thing traveling really fast may each be hard to stop, maybe equally hard to stop. Depends on their momentum, right? Their initial momentum. So it's the same thing here, but we're thinking about something that's rotating. So How hard is it to stop a rotating thing? Well, it depends on how fast it's going and what its moment of inertia is. So that's where you get this I omega, very much like mv for momentum. And I derived this expression for a point mass. We won't use it very often. I did use it in a conservation of momentum problem. So we can do conservation of angular momentum. And the most tangible example I have of this is a figure skater. So here's my picture of a figure skater, right? So initially she has her arms out and one of her skated feet out. That's actually the bigger deal, I think, because there's so much mass there. And maybe she's rotating on the foot that's planted on the ice, right? If she pulls her arms and her foot in, her moment of inertia changes. It gets smaller, right? Because more of her mass is closer to the axis of rotation. So if there's not appreciable external torque, right? That's the requirement for momentum to be conserved, is no external forces. Well, she's spinning on ice, and ice is our like prototypical friction-free surface. So if she's on a frictionless surface, her angular momentum has to stay the same. All right, and so her moment of inertia got smaller, so her angular speed gets higher, right? Omega gets bigger, and that's exactly what you see, right? She spins faster when she pulls her arms in, spins slower when she puts her arms back out. Questions about that? Okay. So let's do an example. I would like to do example number 13, I believe. A 36 kilogram tiger starts at the edge of a 200 kilogram, 4 meter diameter merry-go-round. Rotating at 0.4 revolutions per second, he decides to make his way to the center. What's the new angular velocity? So let's draw a picture. We've got a before, which is a merry-go-round with some radius. Let me match my notation here. Some radius, I don't know, capital R, some omega initial. Can make that a little nicer. And, you know, a tiger. How do you draw a tiger? Oh, I don't know. It's basically a big cat with stripes. Fabulous. All right, so before and afterwards, the tiger is at the center of the merry-go-round. That was supposed to be the body, but now it kind of looks like the head. Oh no, what happened to my tiger? And there should be some omega final. Okay, so if the merry-go-round doesn't experience a whole lot of like friction in its axle, I can assume that angular momentum is conserved. So I will say L initial equals L final. But what are those things? Well, it's I for the merry-go-round times omega initial plus I, what is that? That's, if this is I of the merry-go-round, what is this one? Right, I of the tiger. I got it. Okay. You guys, you got to unmute so I can hear you laugh. Okay, so what is final? Well, it's I merry-go-round plus I for the tiger. Come on, I changed this from a child to a tiger. That's why the tiger is so light. Specifically so I could make that joke every year that I teach this. Okay. So we're just plugging in. And in fact, I could add these together on both sides, right? So I factored out omega final on the right, but they're rotating together. So I could have factored out on the left as well. But it doesn't really matter. So the merry-go-round's not changing its moment of inertia, right? The merry-go-round is not redistributing, but the tiger is moving from the edge to the center. So when he's on the edge, he's a point mass. So let's do this. The merry-go-round is basically a disk, so I'm going to say half m r squared times omega initial. And the tiger is basically a point mass, so I'm going to say m r squared times omega initial. And afterward, the tiger's at the center, so the radius for the tiger afterward is 0. You guys buy that? Okay, so half m r squared times omega final. From here, it's just plugging in numbers. So let me ask, does this make sense to this point?
Yep.
Okay. So yeah, L initial equals L final. I'm just plugging in I omega for each thing and adding them together. And then I has a definition for each of these guys. So then I'm just going to plug in some numbers. So I've got half, what in the world is the mass of 200? Half times 200 kilograms times r squared was, I have this over here, it's a 4 meter diameter, so it's a 2 meter radius squared, times omega initial. Oh, if you multiply by 2 pi, this is in revolutions per second, right? If we go back up here, revolutions per second, and there's 2 pi radians in 1 revolution. So I'm just going to multiply by 2 pi. So that's 2 pi times 0.4 is like 2.5. We're almost there. Times 2.5 radians per second plus, what is this, 36 kilograms times 2 meters squared times 2.5 radians per second equals, shortcut this number again times omega final. Right, so because that's just the merry-go-round again, the merry-go-round didn't change. So if you solve for omega final, you get 3.4 radians per second. Okay, so does that make sense? Well, we started with, what did we say? 2.5 radians per second. The moment of inertia of the system got smaller, so omega got bigger. So yeah, that makes sense. So the next time you're on a merry-go-round with a tiger, notice how the angular speed changes when you guys move around the merry-go-round, one of you is trying to eat the other, I presume. Okay, that's it for chapter 8. So we will move on to chapter 10 on Monday. And again, chapter 9 is all extra credit stuff. The next exam is over 7 and 8. I think it's next Wednesday. So I will probably post that I'll make it available from Monday to maybe Saturday. Reserve the right to change that if I want to, but I think Monday to Saturday makes sense. So unless there are any questions, I think we'll call it good. All right, cool. So thank you guys for your attention, and I'll see you next time.